So like I said, oh, and there are, I guess there's one announcement, which is that the exam is this Friday. It was supposed to say Friday on the syllabus before, but it is fixed now. So you can take the exam any time of the day. We're going to have class just like usual in the morning, and you have until I think like 9 o'clock at night to start the exam, and you get 2 hours for it. So yeah, be sure for the open response to write out your answers as thoroughly as possible, because that's how I'm going to distinguish from the cheaters from the non-cheaters. Let's see. So yeah, they're going to be every other Friday for the rest of the semester, unless at the very end of the semester it doesn't line up so that we have an extra Friday. Then we'll cross that bridge when we do it. Hmm. Okay. All right. This should be good. All right. Yeah. So the last time we talked about separable equations, and we know how to solve those now, basically. So let's go back to an example that we had that was not a separable equation. So this one right here. Okay, so this could not be written. This is not equal to some function that's entirely in terms of x times some function that's entirely in terms of y, no matter how we try to rewrite this thing. So it's not a separable equation. So what can we do in order to solve this thing? Well, excuse me. Let's try to solve a simpler thing first. So if we get rid of this x term, then what we have is just y prime is equal to y. And we already know the general solution to this ODE. So it is y of x is equal to c e to the x. For some constant c. Okay, so the trick that we're going to do in order to solve this is to take this constant c and replace this with a function of x, which we'll call u. So this is called variation of parameters. So this trick is called variation of parameters. So we're going to try to see if we replace this constant c with a function of x, and we allow it to vary with x, can we get a solution, a general solution to the original? So what we'll have is u of x times y of x. Let's do a little rewriting of our notation. Because this is a change of our original equation, we'll call the solution y prime. Or not y prime, y star. So this y star is the solution to the equation when we take out that x term. Okay, so our new general solution, we're hoping to write in terms of some function times our y star. And if we plug this into the original equation, what do we get? We get y star is equal to, now both of these are functions of x, and so we need to use the product rule. So this is, I don't know how to get rid of this. How do I get rid of it? Okay, there we go. Hate using a tablet. Okay, so this is u prime y star plus u y star prime. So that's by the product rule. And this is equal to x plus y, which is x plus u star. And so if I I want to solve for u here. What we have is in this top one, we know what y star prime is. So u prime y star plus u, and then y star prime is just y star. So we'll place this y star, and then we can cancel this out on both sides. And we get u prime y star equal to x. And so what we want to do is, let's see, should I write u prime y star? This is equal to u prime e to the x. So right here, our general solution. And this is equal to x. And so what we get ultimately is u prime is equal to x e to the minus x. So at this point, we can get u of x let's see, let's say by integrating x e to the minus x. And how can we do this? So we can do this by the name of that technique of integration. I can never remember what the, so let's say, where do I get? So the product rule tells us that the derivative of the products is the product of derivatives. So let's write it like fg prime is equal to f prime g plus integration by parts. That's the name. Okay. So we get this. And so we rewrite this thing as, when we integrate both sides and get, by the fundamental theorem of calculus, fg is equal to the integral of f prime g plus the integral of f g prime. And so in this more familiar form, we have the integral of fg prime is equal to fg minus the integral of f prime g. You memorize integration by parts, you already knew this. So I'm telling on myself a little bit there. So the integral of this thing is what we'll call, well, what do we normally call these? U and dv. So this is, we'll call this thing u, call this thing dv. And so du is equal to 1, and v is equal to minus e to the minus x. So the integral of x e to the minus x dx, sorry, dv should be e to the minus x dx. So what we get here is uv, which is minus x e to the minus x, minus the integral of v du. So that's minus e to the minus x plus e to the x dx. So we get minus x e to the minus x plus dx. Okay, so this is our u of x. I trust that if I've made any mistakes, you'll tell me. And so what this gives us for our general solution to recalling our original equation, our original ODE, y prime is equal to x plus y. Our general solution should be minus x e to the minus x plus e to the x plus c times e to the x. And if I just do a little distribution, I'll get minus x plus e to the 2x plus c. I'll give those who are writing a chance to catch up on this. Whenever you're good, just give me a thumbs up. Thumbs up. 1, 2, 3, 4. Okay. And I believe a peace sign as well. So, okay. So this is a specific example of a more general technique of integration. So, or I'm sorry, a technique of solving ordinary differential equations, which is basically integration. Fancy integration. And that is techniques for solving first order linear ODEs. So we know what ODEs are, the stuff we've been doing. We've only been concentrating so far on first order ODEs, so that's the ones with the highest derivative is the first derivative of y. So the only word we're left with is linear. And we actually talked about this, if you recall, on the first day of class. So a linear ODE is one that we can write in the form, let's see, should I write? We'll start off with the nth order linear ODE. So this could be written in the form y, the nth derivative We had a coefficient on this that was a function of x, so I'll call that a n of x plus a n minus 1 of x, y, where this is this represents the nth derivative, right? I'm sure you recall this from previous classes. So it can be written like this, all the way down to, let's say, a2 of x, y double prime, plus a1 of x, y prime, plus a0 of x, y, and this is equal to, what should we call this? We'll call this, what do they call it in the book? Q. We'll call this Q. Okay. So if it's a linear ODE, it can always be rewritten in this form. And the reason it's called linear is because it only has first powers for degree 1 terms in the derivatives y, y prime, y double prime, and so on of y. Okay. So there's no y squared, there's no y prime squared, there's no y times y prime, or y triple prime, y double prime, something like that, right? The derivatives of y only appear as first degree 1 term. So it's like a polynomial. It's like a linear polynomial. The variables, if you take in the linear algebra class, for example, then we can have this equation with lots of variables, but all of the variables are only raised to the power of 1. So that none of them are multiplied by each other, none of them are squared or cubed or anything like that. So that's the sense in which we mean linear. And these are special because they're particularly easy to solve, and they have a lot of nice properties. And so we're only going to look at first order ODEs. And so that's those that just contain this much right here. So just the first order part of a linear ODE. So first order linear ODEs. And so they are, let's say they are anything that can be written as y prime plus p of x y equals q of x. Where this p and q of x are arbitrary functions of x. Going back to our first example from today, y prime is equal to x plus y. We can rewrite this in the standard form that we have for a first order linear ODE by subtracting the y over to the other side. Green. There we go. So y prime minus y equals x. And so in this case, we have e of x is equal to -1 Q of x equal to x. And these have some very nice properties that we'll probably talk about on Friday. But for now, I'll just say that if P and Q are continuous functions, then we have an initial condition, then this initial value problem has a solution. It has a unique solution. But unlike in the general first order ODEs, where it was possible that although we had continuous functions and a continuous partial derivative in a certain region, we didn't necessarily have a unique solution to that entire region, but in some smaller region, possibly around the initial condition. In this case, the solution always exists or always extends to everywhere that we have. The existence and uniqueness extends to wherever we have the conditions apply. So I'll say really quickly why that's true just for continuous functions. If we write this in our original, this is how we were looking at first order ODEs, right? So y prime is just a function of x and y. Then this is equal to q of x minus y p of x. So p, q are continuous. Automatically gives us that f of xy equals q of x minus y p of x continuous. Right, this was our first condition of the existence of uniqueness theorem. So if you take continuous functions and you multiply them together, or you add or subtract them from each other, you again get a continuous function. So the first condition is satisfied. The second condition was that the partial derivative of f with respect to y is also continuous. And so we have that the partial derivative of f with respect to y, this first thing here is just a function of x, so the partial with respect to y of that is just 0. Because y changes, q of x doesn't change at all. And then minus y, p of x is just considered a constant when we take the derivative with respect to y. And so the derivative with respect to y of this is just minus p of x. And so p is continuous. Immediately implies that, sorry, setting a bad example. There we go. The partial derivative of f with respect to y is continuous. So just knowing that p and q are continuous in some region automatically guarantees that we have a solution exists and that it's unique. Okay, so that's the first useful property of these things. What's next? So first order linear ODEs have a straightforward set of solution. So we can find a solution. We can always find a solution in a very straightforward way. And it basically follows exactly what we did in the previous step. Thought you were raising your hand, but that was a cat's tail. Also, we're on Zoom. Um, so the first step. Okay, so actually, there's a little bit of discrepancy between the different texts that we're using for this class. So I'm going to go today by the method that's in the class notes. And there's also a method in the Jury level book, which I will probably talk about tomorrow, if we have enough time. But they're both equivalent. They both work equally well, and they give you the exact same solution. So they're completely equivalent to each other. It's just a matter of personal taste. So the first step of this is to solve what we call the homogeneous version of the linear first order ODE. So we need to know what this means. So a linear, well, yeah, this is just true in general. A linear ODE called homogeneous if q of x is equal to 0. So that was that q of x on the other side. So in other words, it can be written as, we'll write it the same way, an of x, nth derivative of dy. Okay. Down to a1 of x, y prime plus 0 of x, y equal to 0. So this, the thing that makes it homogeneous is this part, 0. The term that just depends on x. So if we throw that part away, and you'll notice when we did y prime is equal to x plus y, that was the part that we threw away, the x part. So that would give us the homogeneous version of this. So we'll solve that. Now, why is this straightforward? Because when we throw away the homogeneous, or sorry, the non-homogeneous term, we get y prime plus e of x y is equal to 0, right? And if we rewrite this as y prime equals minus e of x y, then this is a function just in terms of x. This is a function just in terms of y. So this is separable. And we know how to solve those. If our original ODE was homogeneous, we're done. Otherwise, we move on to step 2. And of course, we do the normal thing with separable ODEs here. We figure out what the stationary solutions are. In this case, y equals 0 is always stationary or equilibrium solution. And then step 2, solve the inhomogeneous or non-homogeneous version of the ODE by variation of parameters. Oh, let me take a step back. So we have something even better in this case. if we go back to this situation right here, and we rewrite this, we go ahead and we solve the separable equation. It's actually going to be really straightforward. So dy dx is equal to minus d of xy. And of course, you can always skip the step where you rewrite this in live form. I'm just doing that for my own sake. We treat this like a fraction and multiply and divide. So we get on one side the integral of dy over y. So of course that gives us a natural log of y, which is we're gonna exponentiate and we get e to the something. And on this side we just have integral of minus d of x dx, right? And because we assumed d of x is continuous in some region around our initial condition x0, y0, then antiderivative exists in that region. So we're entirely free of problems here. We already know how to get the solution, and we know exactly what it is. It's just the integral of minus d of x dx, or ultimately e, right? Like y is equal to e to the integral of d of x dx. Right? So we know what the solution is to the separable, to the homogeneous part. And remember, we called this thing y star, so maybe I should rewrite that as well. Okay, so that's great. We have our solution. We know if, based on the assumptions that we make about this p of x, that everything works out fine here. Okay. So the homogeneous version of this equation is just a separable equation. This is easy. So step 2, when I say easy, I mean easy relative to some other things that we're going to talk about. So step 2 is solve the, and I'm switching back and forth between these questions. Non-homogeneous version by variation of parameters. And how do we do this? We go back to the original equation. We see that y prime is y prime, excuse me, y prime plus p of x times y equals q of x, where q of x now is whatever it originally was. We're going to write y as being u of x times y star of x. Y star is our solution from the homogeneous, you figure that part, homogeneous version. I think I need to remember to talk louder whenever I do these things, because when I went back and watched the recording, I noticed that it's kind of difficult to hear what I'm saying. I think maybe the microphone on this computer is not very good or something. Anyway, so we go back and plug this in, and what we get is u for this y prime. This gives us u prime y star plus u y star prime plus p of x u, all right, give me a second. P of x u y star q of x. And if we go back up here, we see that y star prime is equal to the derivative of e to the integral minus e of x dx, the derivative of e to the integral. Yeah. And so what we get for this is e to the integral. Let's simplify things a little bit. Let's write this. So we'll say that capital P is equal to the integral of p of x dx. So we'll just write its antiderivative as capital P, right? So we can rewrite this thing as e to the minus capital P of x, right? It's just the antiderivative. So simplify this a little bit. Let's write this as e to the minus p of x. And so that is, of course, e to the minus p of x all over again times the derivative of what's on top, which is minus p of x. And so that is just y star, right, the minus p of x times y star. So when we plug that in over here, what do we get? We get u prime y star plus u times minus p of x y star plus p of x u y star is equal to q of x. Based on my reading of facial expressions, I feel like maybe I should pause here for questions. This is the point when having in-person classes would be beneficial and be able to read your body language more accurately. No questions? Pretty straightforward. Okay. So then you know at this step what happens. These two things are just the positive and negative of each other, so they cancel out. And we're just left with u prime y star is equal to u of x. And then we can solve for u by saying u is equal to, well, let's do it in 2 steps. U prime is equal to u of x divided by y star, where y star is our solution version. And then u is, of course, just the antiderivative. And we know this thing exists. We know this thing exists, or there's no problems here in dividing by 0 because we already found our stationary solution, right? Which was y star is equal to 0. So there's no problems performing this integral. Okay, so that was a lot of work to come to the conclusion about how do we solve these first order linear ODEs. So let me summarize this all up. This was meant to be split up among 2 days, and so if we'll use tomorrow for the examples. But to summarize how we do one of these things, number one, so let's start off with y plus or y prime plus p of x y is equal to q of x. All right, so this is the thing that we're trying to solve. So first, solve y prime plus p of x y is equal to 0. So we get y of x is equal to e to the integral of minus p of x dx. Right, where there's an implicit, I'm ignoring the constant. So there should be a constant out front, right? So I'm ignoring that because in the next step we use that for something. So in the next step, oh, I should put a y star there. Indicate that this is the homogeneous version. So next, find y is equal to u y star by doing this integral, which was u of x is equal to the integral of u of x y star over y star of x. Yeah. So really, there's only 2 steps. We went through a lot of work to justify what those 2 steps are, but in the end, this is a pretty straightforward procedure. So we get our homogeneous solution, then we get the part of the solution that gives us our non-homogeneous part, and then we just put them together. That's the solution. And then there's the last step where this gives us, of course, we have a plus c here, and so we need to solve for that c by using the differential equation. That's it. So now maybe we have some time for example. I'll pull one from the book. Oh, that's the one we did in class. Maybe there weren't good ones in this book. Oh, this looks ridiculous. Let's go for it. So, example. X times y prime plus x plus 1 y equals 3x squared e to the minus x. So first off, this is definitely a homogeneous linear equation, linear ODE, first order. Sorry, I said homogeneous. So this is definitely a linear first order ODE. So it's first order because we have a y prime here, we have a y, we have just something in terms of x right here. None of those y's are derivatives. Y's are multiplied by each other. These are our coefficients right here. And then finally, on the right-hand side, we have something that's totally in terms of x. So this is definitely a linear ODE. It's definitely first order. So we can use the technique that we just talked about to solve this. Okay, so I want to put it in the form y prime plus d of x y equals q of x, so that I can apply this method that we just derived. And so all I have to do is divide through by x. I get y prime plus x plus 1 over x. Y is equal to 3x e to the minus x. So we're hoping that this is continuous at x equals 0. So we hope our linear conditions, our initial condition is somewhere away from 0. All right, so we have here e of x is equal to x plus 1 over x, u of x to 3x to the minus x, which is not 0. So this is non-homogeneous. If it was homogeneous, it would just be a separable equation. We wouldn't have to do that. All right. So let me cheat for a minute. Get the book. All right. So we know that our homogeneous solution is going to be e to the integral of e of x dx. And so this part right here, which we were calling capital P of x, this is equal to integral of x plus 1 over x dx, which is the integral of 1 dx plus the integral of x dx. Write this in the fancy way, show how good I think. So this is x. This is natural log of x. Well, we choose, it should be natural log of the absolute value of x. Based on our initial condition, we'll choose whether or not we're using the positive version of x or the negative version of x. So let's say, do they put an initial condition in? Yeah, they say for x greater than 0, x greater than 0. So that allows me to drop that absolute value there. Choose that. And we only need one antiderivative. It doesn't matter. It doesn't matter which one we use. So I'm not throwing the constant integration. So what I get is that this is equal to e to the minus x times e to the minus natural log of x. I should write that out. So this is 1 over x times e to the minus. Just using my exponentiation log rules here to get that this is equal to 1 over x. Okay. Any questions? Remember my threat from earlier in the semester. If nobody ever asks questions, I'm going to just start recording these and sleep in instead of getting up early in the morning. Okay. So the next step, we want y is equal to y star. And so we get u as the antiderivative of u of x over y prime. Keep saying y prime, I mean y star of x dx. So we want the antiderivative of this. So q of x was 3x e to the minus x. And this is all over 1 over x e to the minus x. Things seem to work out very nicely in our favor. Cancellation of the bat. The integral of 3x squared dx x cubed. So we get our And now we'll throw in a constant integration. So that will give us our general solution. So what we ultimately get is multiplying this out. Well, let's not multiply it out. Let's actually show that. X times x cubed plus c is just x. If I get rid of this. There we go. X squared e to the minus x plus c over x. X. That's it. So there's our solution. Now maybe this is an interesting example. I think you probably kind of have the sense of how these problems work now. So I want to do an example that brings up the point of where are these solutions valid? So this is a good one. So we have an initial value problem, y prime minus tangent of x, y is equal to 0. So in this case, we have p of x is equal to minus tangent of x, q of x is equal to 0. So this is a equation. And the other part of the initial value problem is that y of 0 is 2. So remember what I was saying before about the relationship with the existence of unique for this one. Tangent x is, write this over. Tan x is only continuous on finite intervals. So it's only continuous from open intervals. So the endpoints of the discontinuities of tangent happen whenever we get to an odd multiple of pi over 2. So we'll have should I write this? 2n plus 1 times pi over 2 up to 2n plus 3 pi over 2. Right. We only get it in intervals like this. And so when we look at this initial condition, when we have 0 here, then we're only going to have tangent being continuous going out from 0, the farthest we could get our p of x being continuous is from minus pi over 2 pi over 2. So that's where we're looking. It's within this region. In general, when we look at these first order ODEs, this is where our existence and uniqueness theorem would say somewhere inside this interval, a solution exists and it's unique. So as we go outside this interval, we don't know for sure, probably not. But even inside this interval for a general first order ODE, we don't know that the solution exists as unique. Maybe just in a smaller subregion inside that interval. However, for linear ODEs, we know that the solution extends all the way. Well, I'm telling you that that's true. Probably on Friday we'll talk about why that's true. Okay, so this is the interval where we expect our solution to exist, to be unique. Here we go. So let's try to solve this thing. Well, we already know what y should be in this case. We don't need to say y star because this is a homogeneous equation, so this is the solution. The y is equal to e to the integral of tangent x dx. Anybody remember what the tangent is? It's not an easy one. So our solution in general, and because we're doing the homogeneous solution, we can put our constant of integration there. So that's c e to the minus natural log of the absolute value of cosine x. And so when we go from negative pi over 2 to pi over 2, what can we say about cosine? What is cosine of this region?
0.
It's 0 right at the endpoint, but in between, so we're not including the endpoints, right? It's an open interval. So in between,
Okay.
so pi over 2 is negative pi over 2 is straight down, pi over 2 is straight up, right? And so when we swing from minus 90 degrees up, that's in the positive direction, right? For cosine, that's the positive x-axis. I can never remember if zoom does this backwards or not. On the unit circle, going from negative pi over 2 up to pi over 2, that's always in the positive x direction. So cosine is always positive in this region, and so we can just drop these absolute value symbols. And we get c e to the minus cosine of x, or sorry, natural log of cosine of x, right? And so this is just c times 1 over cosine of x, which is, double checking to make sure I didn't mess up, secant of x. Okay, and now we just plug in our initial condition. X is equal to 0, so we get c times cosine of 0 is just 1, so we get c times 1, 2. So our solution y is equal to 2. Now, if we look at this solution, what we see is that we have secant here, and secant also has discontinuities at the same places as discontinuities at odd numbers times pi over 2, because it's 1 over cosine, and cosine is 0 at those points. So what we get in our solution is something it's continuous in the exact same place that our p of x was continuous. So that's what's very useful about it. I've gone exactly 2 minutes over again today, so I'll stop there. I'll stick around if there are any questions, but otherwise I'm going to save the rest for tomorrow. Good to see everyone. See you tomorrow. You have a good day.
Professor, I just had a couple questions about like the additional problems.
Like where can I find solutions for those?
If they're not in the book, you can put them into Wolfram Alpha, or you could do what I would strongly suggest, which is to just write up your solution, send them to me, and I will give you feedback.
Okay. Okay, thank you so much.
No problem.